Yeah, so this is work I've done. I mean, I'm going to talk about sort of overview of a work I've done over the last maybe 10 years with a number of people. So some of whom are named down here: Toby Cubitt, René Audouin, Ebi Long, William Matthews, and Simone Severini. A few of them are not named because I will focus on the communication via classical channels. I think this is more interesting and more apt for the scope of the present workshop. So we're taking a classical communication system and we're looking at how the presence of entanglement or of other non-local correlations can affect the communication. And so the case study, if you want, is we're looking at zero error communication because it's such a serious condition on the communication parameters. So here's the outline, more or less, of the talk. So I will just start very gently with the channels and graphs, because everything traditionally is couched in the graph theoretical language. Then I will discuss how the zero error communication is affected by non-local resources, and in particular, in the third part, how this looks when we have entanglement between the sender and the receiver. I mean, in fact, practically all of the talk will be about point-to-point communication. It's very typical of this kind of investigation. And maybe I'll have to cut a little bit the part 3, because I realized that I put a lot of technical formulaic discussion there. The main point is part 4. Entanglement can actually make a difference. I mean, obviously, this is why I'm giving the talk. So this is sort of the spoiler. There are cases where entanglement between sender and receiver can actually increase the zero error capacity. And so that's sort of a light of hope that entanglement can do something also in systems that are not themselves quantum. And then in the conclusion, we can reflect on a few open questions. So this is how it goes. So in classical communication theory, channel is just a stochastic map between alphabets. And we will just consider them as discrete. So X and Y are discrete sets. In fact, for most of the time, you can think of them finite. And the channel N is just a stochastic map, or otherwise known as a stochastic matrix, a bunch of transition probabilities. And to this matrix, we can associate 2 combinatorial objects. And one of them is called transition graph. It's a bipartite graph that has edges X and Y, so the kind of input and output, vertices input and output, vertices X and Y. And X and Y are connected if and only if the probability to go from X to Y in the channel is positive, and they're not connected if it's 0. So this structure only records the possibility of a transition, not its likelihood. And the confusability graph is a graph, an undirected graph on the input set X. So X is the input alphabet, and it's we have an edge between two. We have an edge between 2 vertices X and X prime, if and only if they can go. They have a possibility of going to the same Y. So I wrote this in a very formal way here. So with the adjacency matrix A, which has zeros where there is in X prime if there is not an edge, and a 1 if there's an edge. And in particular, there are no edges, there are no self loops. So the diagonal of A is 0. 1 plus A is a 0, 1 matrix that is 1 if and only if the inner product of these probability vectors n condition X and n condition X prime is positive, and is 0 if it's 0. And so for the rest of the talk, we're using a particular convention introduced by Lovász. So in the graph, X prime and edge means that X is different from X prime because we don't have loops. But we write X is confusable with X prime if X is equal to X prime, or if it's an edge. X prime is an edge. So this is kind of where, this is precisely where there are ones in this matrix 1 plus A. Okay, examples. So for the typewriter channel, the so-called typewriter channel, you have any number of inputs, and they're confusable. There can be errors with neighboring symbols. So if I put in I don't know, I have to name those 1, 2, 3, 4, 5. These are the inputs. 1 can go to 1 or 2. 2 can go to 2 or 3, 3 to 3 or 4, 4 to 4 or 5, 5, we do it, it's a cyclic typewriter channel, 5 can go to 5 and 1. I don't know, maybe some of the older people here will remember how typewriters worked, and they used to be a cyclic arrangement of letters, a kind of a mechanical device. So if I press a 1, I'm not sure whether a 1 or a 2 will be printed. And so that's so I didn't write the probabilities here because I just directly wrote the transition graph. And the confusability graph is this one, it's the 5 cycle, because neighboring symbols are confusable. 1 and 2 are confusable because they can both end up here. 2 and 3 are confusable because they can both end up here. But 1 and 3 are not confusable because 1 can go to some distribution over 1 and 2, and 3 goes to some distribution over 3 and 4. So they are perfect, I mean, whatever the probabilities are, they are perfectly distinguishable. Another example, the typewriter graph with 3 symbols. So it's this transition graph. The confusability graph is simply the complete graph on 3 vertices, or the 3 cycle. So just a remark, just as we lose information going from the noisy channel going to the transition graph, because we lose the information of the value of the probability, we just record whether it's 0 or non-zero. There is also a coarse graining when we go from the transition graph to the confusability graph, because these 2 channels here, the one here, the picture I wrote down here below is another transition graph. They have the same confusability graph. This is a channel that maps every input symbol to the same output symbol. And okay, so of course also here any pair of symbols is confusable, so we have the maximum, the complete graph as confusability graph. Oops. So then we are also looking at capacity. I mean, basically following a bit a paper by Shannon from the 50s, where he introduced this kind of zero error point of view. In information theory, it's very common to look at many uncorrelated instances of the channel. If you have a product, and if you have many instances of the channel, the most simple assumption is the product noise. So the transition probabilities multiply. And so that translates into very simple formulas for the graphs. For the transition graph, it's simply the Kronecker product of the individual transition graphs. Because I mean, yeah, we have a transition, we have this product is 0 if and only if one of them is 0. And also the confusability graph is similar. So if you write, I mean, always I write it in the form of the adjacency matrix. If I write the adjacency matrix of this n times n prime plus identity, that's the tensor product or Kronecker product of the 2, 1 plus a and 1 plus a prime of the 2 channels. And so this first one is kind of very simple. Okay, it's just the Kronecker product. It's simply I have a transition if and only if a transition in both of the channels. For the confusability graph on the input alphabet, this is known as the strong graph product. We will only look at this one. So whenever I have a graph product, which I write like this, G times G prime, it's the strong graph product. But in graph theory, there are a ton of different products between graphs considered, and so that's why they have a special name for it. So okay, zero error transmission. Well, in transmission, we need to encode messages and we want to decode them. So we want to associate to a message I an input X, which is a function of I, then it goes through the channel and then comes out Y, which is something according to the distribution N of Y given X. And so we want to be sure that the decoder can uniquely and without error identify I, the message I. And so that when you think about it, this means precisely that this f of I must be pairwise non-confusable in the confusability graph G. And so this is this is called an independent set in the jargon of graph theory. And so we're looking at obviously we're looking at maximizing the number of messages we can encode. That's always our problem in this game. We're looking for the maximum size of an independent set, and this is called alpha of G. Again, this is an established notation in graph theory, so people love to have kind of fixed notation. This is a horrible news because in general, I mean, once you're given the graph, you think, okay, now it's just a combinatorial problem, but this is NP complete. So like in general, basically we can give up hope to find this number or to find find an independent set. In practice, of course, we will still try it. We'll try to get some independent sets. We get lower bounds on alpha, and we also want upper bounds. And so Shannon, when he started this business in '56, he didn't know about NP completeness, but people had a good feel about computationally hard and not so hard problems. So he almost immediately looked at how to make the problem easier. And so one of the things that he did is he considered instantaneous feedback between channel users. So like Shannon would, he didn't just look at one instance of the channel, but at kind of multiple uses of the channel, which he thought of sequential. So you first use N, then you get the output, then you use N again, you get another output. And in between the channel uses, you could have noiseless instantaneous feedback from the receiver to the sender. And that's kind of, turns out that simplifies the analysis a lot. So that's kind of the main part of his paper is actually the analysis of this feedback scenario. Here, what I promised in the abstract is we're looking at the impact of pre-shared correlations between the sender and the receiver. And so in a purely classical world, that doesn't seem to lead anywhere, because in a purely classical world, such correlations can only be thought of as pre-shared randomness, some shared random variable that has to be shared before, and you can convince yourself this will not affect the zero error capacity of the channel, and so it doesn't change alpha. But yeah, as we see with quantum mechanics and beyond, there are other ways of thinking about these correlations. And so yeah, to stay within the classical world, first of all, I don't even want to go into entanglement. I mean, the kind of correlation we're looking at is mathematically simply a bidirectional channel. It's something with two inputs and two outputs. But additionally, we want to make sure that this object itself, this P, this is a stochastic matrix, P of UV given ST. This should not allow signaling between the senders and between the two parties. So incidentally, these kind of objects were also studied by Shannon in the early days of information theory as one of the very first examples of a multi-user channel, and he observed, okay, it's horribly difficult. He didn't look at cases where you don't have signaling, because those have capacity 0 in either direction, so they were maybe considered non-interesting, but turns out they are actually very interesting. And I refer you to a wonderful paper by Jonathan Barrett from 2007, not for the priority, but more for the kind of a consistent view and the review of the information theory of these no signaling channels. Okay, so I probably have to look a little bit how I'm doing with time. So what can Alice and Bob do with such a correlation? So I mean, I assume that Alice and Bob, they have some kind of terminals. Alice has a device where she can plug in S, and Bob has a device where he can plug in T, and they get out U and V. It's a probability distribution, so it's a kind of positive numbers, non-negative numbers that for each S and T they sum to 1. But in addition, we want this no signaling. So what this means is that the conditional distribution, for example, of Bob of seeing a V given T, that's kind of his worldview, is not affected by what Alice does. So if he doesn't see Alice's input and Alice's output, what we do is we just fix Alice's input and we sum over Alice's output. That's this marginal here. This should be equal to something that does not depend on S. And so we can just denote it as a probability of V given T, and vice versa for Alice. So these are just linear conditions, and you can ask yourself, okay, what are the kind of channels that I get that meet these conditions? First of all, you see, okay, these are just linear and non-inequality conditions, so that's a convex set. In fact, it's a polytope, and the extremal points are of very interesting structure and have been studied in a number of different contexts, including the foundations of quantum mechanics. So a very important conceptual point is this one. So I'm going to read this out. Also, formally a channel with two simultaneous inputs, the no signaling condition shows that we can conceptually think of it as in a different way. We can think of it as a kind of Alice having a black box that she can use without having to wait for Bob's input. So the second probability, this second no signaling condition here, this ensures that there's a well-defined probability distribution of U given S, regardless of what Bob does. So we can entertain the fancy that, yeah, sure, okay, so we use the device without waiting for Bob. And then Alice has fixed her input and output, and then Bob is left with a conditional channel that we can write in this way down here, simply according to Bayes' rule. We simply divide by, we simply write a new conditional probability of V given S, T, and U. Of course, he doesn't know S and U, but this is a description that we have of the situation. Given Alice sees S and U, or given, maybe this is, you can say this might be Alice's description of Bob's channel. Bob's channel, of course, from his point of view, is still just this one here. This is a convex combination of such objects. Okay, that's a very important thing to say, because we want to use this device now in conjunction with a channel, where Alice will have to use her box first and Bob afterwards, after receiving the channel output. But before I go there, I just want to review a little bit the structure of these kind of correlations as we know them from the foundations of quantum mechanics. So, like we started, when we are in a purely classical world, we think about how can such an object come about if there's no communication between the parties. Obviously, we designed it in such a way that the P does not provide communication capabilities. If we conceive of this a little bit stronger, we say, we don't want P to have any communication involved at all. I think you will inevitably arrive at the idea that, okay, it has to be built on pre-shared randomness, pre-shared hidden variable lambda between them, and then lambda will inform what happens locally. So for each lambda, there is a local channel A lambda given U of U given S, and a B lambda of V given T. And then we simply take a mixture over those lambdas according to some probability distribution. And we are exactly in the kind of mindset of Bell's local hidden variable theories. The kind of correlations you get is exactly the convex hull of product channels. A, B functions. Oh yeah, well, okay, maybe this is confusing. Maybe I shouldn't have written it. A, B are just channels, and the extremal points are when they are deterministic channels. And so that U is a function of S or V is a function of T, but that's I think it's unimportant. The local invariable, the local channels are just a convex hull of tensor product channels. And so that's a subset, but it turns out it's strict. Another very important subset, the one that this whole conference is about, basically is the correlations we can get from entanglement and local measurements. And so in a very simple-minded way, I can just write them like this. So I have each of the parties has their own quantum system with their own Hilbert space, and they have their own observables, measurement operators. They have they share an entangled state, so that's kind of lambda is converted into this shared random entangled state that has been produced before. That is an entangled state between those two Hilbert spaces. And then I can write the probability of given input S and T of observing U and V as this trace here according to the Born rule. And so you can convince yourself quite easily that you have this kind of inclusion, that the local invariable, the local correlations are contained in the quantum correlation, are contained in the no signaling correlation. I should say, this is a kind of a naive way of writing it. By now, the sophisticated research has gone on to distinguish at least 4 different kinds of sets of quantum correlations that subtly or not so subtly differ from each other. A priori, we can ask the following questions for any of them, but let's just stick with this one here. Most of the time, it will be enough to even consider finite dimensional Hilbert spaces, just as we stick with finite alphabets for the communication scenario. And yeah, so the wonderful insight of Bell and of subsequent analysis, Bell and Sirelson, was that all of those inclusions are strict. The local correlations are strictly contained in the quantum correlation, are strictly contained in no signaling, and it's enough to go to binary input S and T and binary output U and V. And so the proof for this is actually exactly, so the Bell inequality or the Tirielson bound, what you do is you're looking at a particular functional that you, a linear function that you maximize over each of those classes, and it's this one here. So for uniform input S and T, consider the probability that the XOR of U and V is equal to the product of S and T. And so the maximum of this for the local ones is 3/4. It's a kind of a combinatorial argument. It's a geometric argument due to Tirielson that the maximum of a Q is this cos square of pi over 8, which is roughly 0.85, and the maximum of a no signaling is 1. And so yeah, so these calculations are elementary, and they prove that those classes are very distinct. And well, okay, they kind of, and just if you don't know a lot about non-locality or quantum non-locality, I refer you to a review paper by Nicolas Brunet et al. From a few years ago, where many more of such interesting separations are discussed. So how to use a channel in conjunction with such a given no signaling correlation? Okay, so we have basically two channels, right? We have this two input to output channel, and we have the noisy channel. So I did something here in the yellow part for this P. I flipped the flow of the output side, right? So the input S is here, and the input T is down here on the right-hand side. And you will see why, because when you think about how can I use this, well, I mean, Alice has a message, and she will have to eventually produce an input to the channel. And so the only reasonable way of doing this is first use the correlation to produce an input S to the non-local resource, get an output U, compute an input X to the channel. Now the channel does something random, gives an output Y to Bob, and Bob will now have to use his terminal of P, this box here, and produce an input T, plug it in, and eventually get an output V. And then from this here, he will have to compute an estimate of the message that Alice was intending to send. And so yeah, these magenta arrows, these are Alice's mappings. These are computations that she has to do based on the data that she received or that she's producing in the process. And these are computations that Bob has to do. And so I repeat, this is well defined despite the weird ordering, because there is a well-defined channel of mapping S to U. And once this is done, there's a well-defined channel conditioned on that mapping T to V. Yeah. So this comes from the fact that we have no signaling correlation. It comes from the fact there's no signaling from Bob to Alice. And of course, in addition, we also have no signaling from Alice to Bob, because we want that all the causal influence in the system is due to the channel, to this white object down here. Anything that Bob can learn from Alice about her intentions must come from here. Okay, so now I go to another picture where I just absorb all these local computations into the correlation. So I just make a new non-local correlation, or a new bidirectional channel where the input is directly I and the output of Alice is directly X, and vice versa. The input of Bob is directly Y, the channel output, and the output of P prime is J. And so this is justified because if P is, for example, local, then P prime is local. The composition of a local channel with these local operations is also a local object. If it's quantum, if P was quantum, then P prime is quantum, is a quantum correlation. And if P is no signaling, then P prime is no signaling. Just have to convince yourself that this is true. And so now we are interested in zero error communication. So that would mean that we have to we want to make such a scheme where J is equal to I with probability 1. So what does that mean? That means that if there is a possible transition from X to Y, then it should be impossible that J is different from I. So impossible in the sense that the probabilities, the probability, oops, yeah, now I see what the problem is. I have here my simplified P prime. I should have put it also here. because I want to express the condition in terms of this p prime. So for the condition is a combinatorial one. For all edges in the transition graph xy, and for all I different from j, p prime of xj given I y should be 0. And that's an additional constraint on this no signaling correlation. And then I say, well, the maximum number of messages that I have, that I can have, this is what I'm interested in, and let's call this alpha bar of gamma. I mean, pretty randomly. I mean, I just needed a notation to distinguish it from the ordinary independence number. I mean, it depends on gamma by the way we analyzed it right here. So obviously, a priori, I wrote here the channel, but when you think about it, okay, it only depends on the transition graph. And so, yeah, we just have here this formula. So we can also just take this as the definition. The alpha bar of gamma is the maximum M such that there exists a no signaling correlation, P of xj given iy, where I and j run from 1 to m, x and y are from the graph, such that this condition is satisfied. And so, yeah, so we can, I mean, this kind of number can be computed, turns out. I mean, from the form of this formula, you see this can be tested by linear programming. In fact, itself, it's a linear program. So it turns out this alpha bar is the integer part of the so-called fractional packing number of gamma. And this is written here. So fractional packing is a rational relaxation of the packing number of the independence number. So it's itself this is itself a linear program. Then alpha star of gamma is the sum, you maximize the sum of weights wx. They're non-negative, and for each y, you want that so for each y, you look at this sum here, sum gamma given of y given x of wx. This is all the x's that can go to y possibly, right? Because for all other x's, this gamma is 0. This is the adjacency matrix. This should be less than or equal to 1. And so, yeah. So this we can characterize completely. This is very unlike all the previous, like this previous story of the Shannon zero error capacity where we are stuck with the independence number that's NP complete. This is a linear program which is efficiently computable. And so, yeah, little remark of this fractional packing number. This was studied already by Shannon in his founding paper of the zero error communication theory, and it turns out to be essentially equal to the feedback assisted zero error capacity. Notice that this is here one shot. We just use we use the channel one time and we get this number. And so the fractional packing number also has plenty of nice properties, but I mean, let's not go into this. So more importantly, if we should discuss a little bit what happens if we have quantum correlations, because these no signaling correlations, they're very nice mathematically, but we don't really know how to think about them operationally. For quantum correlations, we know that because we say, okay, there's kind of prior to the communication, the parties have to share an entangled state, and then they just act locally with quantum operations. And so if we do that, so I kind of open the yellow box and make it a red box now, where we have this quantum state here and the local measurements. So there's kind of all quantum machinery in this red part. If we optimize over all possible quantum ways of building such correlations, the maximum number of messages now for P, not in this no signaling set, but in the set Q, let's call this alpha tilde. Okay, so this is, and I think I should really speed up a little bit. First insight, which I'm actually, unfortunately, I don't even go into discussing. You have to just take my word for it or look up at the papers. Unlike the no signaling variant alpha bar, this number alpha tilde depends only on G. So remember that the confusability graph is not unique to the transition graph. There are many different transition graphs, gamma, that can lead to the same confusability graph. Alpha bar non-trivially depends on gamma. You cannot write it as a function of G. Alpha tilde, you can write as a function of G. That's a very important thing. That makes it more like the usual independence number. And okay, so yeah, I'm sorry for writing this slide because I think I really should get on with this. I feel a little bit bad trying to decode, well, or rather to go through these formulas. I mean, this is very nice once you're in the right kind of mindset, but I wonder if I should not push on a little bit. I think I'll just leave it here. So let me just say the following. So this is an algebraic way of reformulating alpha tilde of G, which kind of manifestly only refers to the confusability graph. It's a very complicated way of writing. It's still a maximization of an integer, such that you have matrices S and then SIX for all X from the graph and all I from the messages, with a lot of different algebraic constraints. Not linear, but kind of bilinear or quadratic constraints. And these are just complex matrices. And so the quantum nature of this definition is in the fact that we have matrices, and in particular that they don't necessarily commute, apart from the fact that I have certain matrices do commute because their products are zero. If you insist that they commute, you are basically, what you're doing is, in the language of the very old quantum theory, you're replacing Q numbers with C numbers. So the simplest case is that if these S and SIX are actually complex numbers, then if you insist that they're numbers, you recover exactly alpha of G. So this is something that algebraists like a lot. So this is kind of an algebraic way of saying, oh, this is like a quantum independence number. You just write algebraic conditions for an algebraic characterization for alpha, and then you simply forget about the fact that you have commuting numbers, but that these are objects from some weird algebra, and they don't commute anymore. That can be very appealing, but like I admit that on first sight, these conditions are a mouthful. By definition, anyway, we have this chain of inequalities, because this is the maximum of number of messages when I have no correlations or only local correlations. This is the maximum when I have quantum correlations, and this is the alpha bar is the maximum when I have no signaling correlations. I just would say that alpha tilde in many ways is even worse than alpha, because whereas alpha was NP hard or NP complete, and the alpha bar is well, it's a linear program, so in a certain sense it's polynomial time. Alpha tilde is not even known to be computable, and very likely it's not computable in the light of recent results. So a very immediate thing is, okay, you have to look for relaxations. I mean, if you want to have anything to say about this number, you have to get away from this general form here. And so Salman Begi came up with this here. So he relaxed this to a semi-definite program where we only talk about inner products of vectors. So this is a bunch of conditions of gram matrices, of a big gram matrix. And this beta of G, the Begi number, is the maximum n such that there are vectors that satisfy these conditions. And so, yeah, so this is an STP, but it's actually even nicer. It's not only can be checked by an STP, but it can be calculated by an STP. So this beta of G is the integer part of a well-known parameter since the 70s, is Lovász theta number of a graph, which is this one here. So it's kind of this very simple maximum trace of Bj, where B is a positive semi-definite variable with trace 1, and Bxy, so this is a matrix that where the rows and columns are indexed by the graph vertices. Bxy is 0 when you have an edge in the graph. So we have this kind of chain of inequality, and so, for example, we can see that these numbers here, they are actually non-trivial. I mean, these for the typewriter channel. It turns out that all the independence numbers are 2. This is not so difficult, but for example, the fractional packet number is 5/2, and the theta number is square root of 5 for the corresponding pentagon. So yeah, one thing that we don't know, actually, I just want to flag an open question. Is there an operational interpretation of this beta number in terms of, for example, restricting the available correlations to some set between Q and no signaling? Because we don't know, I mean, it might be that beta is always equal to alpha tilde, but I doubt it. No, actually it's not, There are gaps, so this kind of is different, sorry. And so yeah, so then one thing that we can do in the spirit of Shannon is we can look at the many copy limit. So then we have many products of channels. We have this products of graphs, and we're looking at the asymptotic behavior of this independence number, and so we call this the zero error capacity. It's assisted by entanglement, and so we find that this is upper bound by the log of the theta number. And okay, this is of course larger than the unassisted capacity. And similarly, we have an even larger number, the zero error no signaling assisted capacity, which is equal to the log of the fractional packing number. Okay, so this is the most important part of the talk. So I just try to get to the conclusions too. We have these inequalities for the independence numbers and for the corresponding asymptotic capacities. The most important message comes at the end. These inequalities both can be strict. There are examples of graphs where you have strict inequalities. I mean, we have also other examples of graphs where there's equality, but those are of course less interesting for the present context. And so this was proved the first one was proved in a paper that I wrote with Toby Kubit. The second one was Debbie Lung et al. A couple of years later. And yeah, so indeed, this is an important remark. We have this inequality that alpha tilde is less than or equal to the famous Lovász number, but in the examples that we constructed for those separations, we actually have equality here. We have equality with the integer part. And so that points to a kind of a limitation to our constructions. So I don't know if you have time to talk a little bit about the construction. I mean, one particular construction goes like this. So you're looking at a graph with 24 vertices here. And I drew it here. It's a graph that is made up of 6 cliques, actually. So each of these groups, alpha, beta, through zeta, are actually K4. They're complete graphs. And in fact, this graph is the orthogonality graph of a specific set of vectors in 4-dimensional space. So each of these bunches here corresponds to a basis, but then there are also additional orthogonal bases, but then there are additional orthogonalities between vectors from one basis and the next. And those things are geometrically very interesting, of course, and also very important in the discussion of non-contextuality in quantum mechanics. So this is called a Cauchy-Specker set. And yeah, so the entanglement is simply a 4x4 maximally entangled state, and the messages are alpha, beta, gamma, delta, epsilon, and theta. And so for Alice to send a message, she will basically just measure the basis corresponding to, let's say, alpha. That's her message. She gets an output, and then she simply plugs in the corresponding point into the channel. So these 24 points. These are the letters from her input alphabet. And then the graph basically just says what are the confusabilities. So we can, for example, think that Bob's output is simply an edge. So he simply gets, like, for example, if Alice's output is 3, she might, the channel will tell Bob, well, the input was either 3 or this one here, over here, because they're connected by an edge. But because they're connected by an edge, the corresponding vectors are orthogonal. So there's a measurement that distinguishes the corresponding post-measurement states perfectly. And so then Bob, by making the correct measurement, can figure out which of the 6 messages was sent. Turns out this graph is independence number 5, though. And so alpha is 5, alpha tilde is 6. And so to wrap up, or to kind of get close to the conclusions, We don't know what this alpha tilde is, so we worked a lot in the past on getting upper bound. So it turns out that a slight improvement of the Lovász number due to Schrijver, the reduced theta number, theta minus, which is basically just the same SDP with an additional positivity constraint. Turns out this is also an upper bound on the alpha tilde. Okay, so the separations there were all due to knowing that alpha of G is less than or equal to something called the Haemers bound, which I also wrote here. It's a completely different kind of thing. It's not an SDP at all. It's actually a minimization of a rank. It's very hard to characterize in general, but it has many nice properties. And so we get that. Okay, so the zero error capacity of the graph is not only upper bound by the log of the theta of G, but it's upper bound by the regularization of theta minus of many copies of G, many strong graph products of G. And so this is itself less than or equal to log theta of G, and it's actually a major open question to decide whether this is an equality sign here. And so here I'm at the conclusion. So again, exactly, I'm already 1 minute over time. So let me just offer some reflections on what I told you now. So this was sort of an overview of past results. I mean, I hope if you're interested, you might go to read some of the papers. The important message is, of course, the entanglement can increase the zero error capacity, both one-shot and asymptotic, of purely classical channel. And all known, so here I'm starting with open question. All known examples use maximally entangled states. I mean, all constructions of schemes. And we don't know if there's any use for non-maximal entanglement. Is there in any channel where I can do something strictly better using non-maximal entanglement? Second point, we have this inequality. The zero error capacity assisted by entanglement is less than log theta of G. Is that an equality? I would say maybe not, but we would need a kind of another bound, a different kind of upper bound that separates them. However, on the other hand, for people who think maybe it is, if you have quantum no signaling correlations between the two parties, then it is, which is a result of myself with Runyaud 1 from a few years ago. So the quantum no signaling assisted zero error capacity of G is equal to log of theta, which is amazing or sort of weird, depending how you look at it. Another reflection is, note that, I mean, this was all zero error capacity. So if you go to the usual noisy channel capacity, so the familiar formula with the maximum mutual information, this is not increased by any entanglement or even no signaling. However, the above, the previous results, they show that at least what can change is the error probability in a given one or finite copy limit setting. And this was explored in a paper by Will Matthews and others, and if they did it in an experiment. So zero, it's not about this idealization of zero error. Like what really happens is that you're changing the error probability. And that already can be interesting. And so yeah, for multi-user channels, we know even that entanglement can make a difference on the noisy channel capacity itself for like asymptotically vanishing error, which was when, like, I refer you to two papers, one by Felix Levitsky and the other by our chair Janis Nötzl. And so that's kind of where the potential lies, I would say, of entanglement in this kind of settings. I think I repeat, why this is exciting is precisely because the system itself is classical. We use entanglement as a kind of an additional plugin that was not foreseen when the system was designed. And that I stop here. Thank you very much.